Suppose you were, very legally, downloading your favorite movie, Shrek 2, off the internet. The data encoding the movie can be broken down into many packets of information. The packets will need to travel from some server, through the internet, all the way to your laptop. Let's say the data can move via a network of connections. However, each connection has a certain capacity for how much data can be transferred over it. We want to make sure you get your movie fast. How do we optimally route the data? This is the problem of network flows. Let's formalize it. The input here will be a directed graph G. We'll also need to specify the source node S and the sink or target node T. We'll be sending the data, or flow, from S to T. We'll also take in as input a capacity function C, which assigns a capacity to each edge. I'm going to restrict the capacities here to be non-negative integers, but this doesn't have to be the case. We want to figure out how to send flow from S to T. That is, we want to find the best collection of S to T paths, along with how much flow to send along these paths. Before we proceed, I think it's worth recognizing just how hard this problem is. Notice that there could be an exponential number of S to T paths. If the solution requires using all of these, we'd need exponential time just to write the answer down. So, is this hopeless? Should we be showing that this problem is NP-complete? No. With a clever idea, we can save ourselves from the NP-hard abyss. Something worth realizing is that while the motivating problem suggests listing out which paths we're using and how much flow to push along them, we can compress the answer by just recording the flow along each edge rather than each path. Formally, our output will be a flow function f, which for a given edge returns how much flow we're pushing through that edge. Remember that edges are directed in a flow network, so this is unambiguous. Notice that there are two things our flow function needs to be valid. First, it can't push more flow than the capacity on each edge. That comes straight from the problem. Second, we need the flow coming into each node equal to the flow coming out. Why? Well, remember that we're sending data from S to T. If this restriction was broken, it would mean that some intermediate node is either creating or consuming data. That doesn't really make sense in the context of our max flow formulation. Let's see a quick example of a flow function. Suppose that this is our network. Let's say we send just one unit of flow along this path. Then, what does our flow function look like? Well, for the black edges, it's going to be 0. There's no flow going along them. The orange edges will all have a flow value of 1, since there's 1 unit of flow going across each of them. Now that we've established that, how do we proceed? It's tempting to try something greedy. Consider the following algorithm. Find a path from S to T, using DFS for example. If alpha is the smallest capacity on this path, send alpha flow along it. That is, increase f of uv by alpha for every edge uv on this path. Decrease the capacity by alpha for every edge on the path. If an edge has capacity 0, delete it. Repeat this until there are no more S to T paths. This seems pretty reasonable. However, a small example shows that this won't get you the optimal max flow. Let's say we find the same path in step 1 and send a unit of flow along there. Then we delete the edges with no more capacity and we're done. But it's clear that this isn't the best way to route the flow. What's happening here? It looks like we made a mistake by sending flow through this middle edge. Now you might think that this problem requires some sort of long-distance planning, and maybe a clever dynamic program can solve it. But there's actually a tiny modification to this greedy approach that helps the algorithm find the true max flow. What if we kept track of the flow that we've pushed and built into our network the ability to take back any moves that we make? Here's the idea. Every time we push flow along some set of edges, let's add back edges with capacity equal to the flow we've pushed along their corresponding forward edges. Then, when we update our flow function, we subtract flow from the edge if it's a back edge instead of adding it. This signifies taking back, sending some flow along that edge. And this is the Ford-Fulkerson algorithm. This is all a little hard to parse. Let's see an example using the same graph we've been working with. Let's say we find that same troublesome path in step 1. Then we do our update, deleting these edges and replacing them with back edges. Also updating the new flow function. Now, in our next iteration, we find this path, which now includes a back edge. This is the step where we reroute a unit of flow back along this AB edge. We'll restore the original edge since it's still a possible option for the future, and we'll update the flow function so that we're not pushing any more flow along the AB edge. Next, we'll continue along this path, deleting this edge and updating our flow function. And there it is. It really works. By having back edges built into the graph, every time we find an S to T path, we really do increase the value of our flow. Some people call these paths augmenting paths, since every time we find one, we successfully increase the flow that we send. You'll also sometimes hear this graph with the back edges called the residual graph of G, given our flow function f. And that's it. That's Ford-Fulkerson. I think it's really easy to get bogged down in the formal proofs as to why this works, but the idea is actually really simple. Try to push flow along a path, and if you do, give yourself the opportunity to take back that move in the future. As you push your flow, just record if that's coming from the source via forward edges, or if it's coming from some other flow you've already pushed. These are backwards edges. If you're still watching, I just wanted to say thanks. This is the first math video I've made. I had a lot of fun doing it, and I hope you like this colorful grid animation thing.